Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to Groundwater Hydrology and Management NPTEL course. This is week 3 and lecture 3. In the week 3, we are looking at the major concepts and about physical groundwater hydrology. What are the major components that is needed to understand groundwater hydrology? In the last lecture, we looked at the hydrogeological map of India, which is made by the Central Groundwater Board. And since it is a static map, which means it doesn't change much, you could see different years of this publication. I've used the recent one from the recent book. And what you see here is a map of India, which demarcates the different geological aspects related to groundwater hydrology. In the last class, we looked at the fact that the aquifer is a function of the geology and the porosity and the porous space present inside. In continuation, we look at this map to understand the different formations in India. Remember that this may not be the same across the world, so you would need to understand different geological settings. But since this course would focus mostly on Indian groundwater issues, we would be discussing this map. First, let's look at the blue color. The blue color is the highest water yielding aquifers, and it is given as a rate of yield in liters per second. And if you look at these blue regions, you could clearly understand that these coincide with the regions where there are massive or big rivers and streams, good water bodies in short. So this would be your Ganges Basin, the Brahmaputra on this side, the Kaveri Basin here, Narmada, Tapti, all are good rivers that are perennial and also have good water potential, surface water. So the ideology is with good surface water potential, there is also good groundwater potential. And these also demarcate unconsolidated formations. When we say formations, it is the formation of the geological unit or the rock, and they are mostly unconsolidated, which means they are not packed, jam-packed, or it has a structure. It is broken in some areas and not broken, irregular, and that irregularity causes a lot of space in between the rocks. For example, if you have platy rocks like plates, it will be jammed together and the space between the rock is very less. But if you have uneven rocks like this, then you have space in between the rocks. And that space is important to store water. And that is why you'll have more water stored in these kind of porous material. And it also depends on where it is located. Because you have a water flowing in these regions, the water can easily enter your formations. And the formations have the potential to store it for a long time. And that is why you can extract it. So the groundwater potential is very high. From greater than 40 liters per second to less than 10 liters per second. So all these blue regions, and then this region has less than 10. This is your Indus Valley region, and most of your blue coincides with the flowing rivers, the massive flowing rivers of the Indus, the Ganges, the Brahmaputra, etc., Kaveri. Moving on, but that is not the major in terms of area. It is not the major aquifers in India. What is the major is the yellow-green color, which is in the central parts of India, and that correlates to the consolidated or semi-consolidated formations, which means it is either arranged in a particular matrix, the soil, and the solid particles, or it is semi-arranged. So when it is semi-arranged or arranged in a particular fashion, then the porous space is less. So when the porous space, the space where water can enter is less, then the extraction is also less. So this is the understanding that the Central Groundwater Board wanted to give a hydrological map, which is based on the porous space as a function of the consolidation of the formations. And the hilly areas are very, very low. Eventually, there's no pore space in the hilly areas, so it is less than 1. If you look at the green color, that is where you have more space for water to enter within the consolidated and semi-consolidated, and it has 1 to 25 liters per second, mostly Rajasthan, Kerala, Maharashtra regions. And then you have the other regions yellow, where it is mostly in the central parts of India. Okay. And the underlying fact here is we need to understand where the formations are and how much water yield can be taken, so that you don't overstress the aquifer system. That note, since we have looked at the porous space is important, we've looked at what is an aquifer, and we've looked at what is a confining unit and the different aquifers in the second lecture. So let's jump into the recharge aspect. How does groundwater recharge happen? I'm going to be very brief here because we have a week just to discuss the recharge and discharge aspects. So the groundwater recharge is the process by which the rainfall or any other surface water body gives water into the ground, into the aquifer unit. So as I said, the aquifer is a unit of storage, and if water comes in, it is recharge. If you lose water, it is discharge. So the recharge area is almost on the top surface, and it is a surface where land use, land cover should be managed to slow down the water and recharge. Okay, so you have trees and plants that can slow down the surface water, like rainfall, it can be slowed down, runoff can be slowed down and recharge. Once it recharges, it forms the imaginary water table. As I said, it is the line at which the water level is kept along the aquifer. So here horizontally, this is one aquifer. Let me turn on my pointer. This is one aquifer. This is number 2 aquifer and number 3. And what you have here is a combination of 3 aquifer systems which are divided by confining units. It can be called as an aquitard, aquilude, confining bed. Different names are existing. Okay, so the major objective of my presenting of this particular slide is not about the recharge process, but the recharge time. So you can see here clearly that the recharge happens from the top. Okay, the first layer is the unconfined layer where water can easily come in from the surface. There are multiple regions where the recharge can happen. Okay, there's multiple regions. Rainfall goes in, groundwater gets recharged, and it gets extracted in your pump. Same way this side, rainfall comes in, groundwater gets recharged, and then goes into the stream as base flow. So now how long does this take? This takes anywhere from days to years, because there's a good area contributing to the recharge. Contributing as in all along the area you have recharge points. So it can go in, and the distance that it has to cover is very small to get into the water table, which is only this distance. Okay, so you have a very small distance to cover so that through gravity it moves down and then mixes with the water table. This takes anywhere from days to years. Now, if you have a good rainfall year, so which aquifer would recharge? It is this shallow or unconfined aquifer, because rainfall happens within 5 days, 6 days, it can recharge into your system. The farmers are happy to see the water in the wells. Then I hit a groundwater confining unit along the conceptual model. What we see as we go down deeper, you see a confining unit, and that confines the upper unconfined aquifer, and below that another aquifer, which is called the confined aquifer. So this aquifer or soil or geological material or matrix has water in it in the pore spaces. However, it is confined on the top and bottom by a confining unit. So it is called a confined aquifer. So now the recharge water has to go through the surface, go into the zone of aeration. This is a zone of aeration where still air is present, go into a zone of saturation and then come down. This takes longer than the unconfined aquifer. How long? It can take more than many years. And so it can be anywhere from a lot of years, decades to centuries, 100 years. And this water can also contribute to the stream flow down the area. Okay, it cannot be readily accessed in this image by the well, because the well is being separated by the confining unit. Then we go down to another impervious layer until the bedrock, and you see another confined aquifer. So 3 aquifers are there. One is unconfined and 2 confined aquifers. As we move deeper, the deepest confined aquifer takes very less recharge from the top, because water takes a long time to come down and it is impervious, so only some water can go through. Whatever the impervious layer is, still some water can pass through because of gravity. And that water does take a millennia, which means 1,000 years to move down. And that is the concern here. If a water takes 1,000 years to move down, and you put a well here because of science and technology, you can easily access the groundwater. Then the problem is you'll take all the water out suddenly, and there's no water in the aquifer. So this water can also go into the streams and can support your trees and plants when it is being pulled up. So this is a slide on the recharge time and some parts of the processes of recharge. Now a question can come: how many unconfined units can a system have, and how many confined units can a system have? Let's answer the second question first. The number of confined units can be plenty. It can depend on the number of confining layers. So we don't know unless we drill down and see how many layers in the cake. We don't know how many layers are put in. So it depends. And using a geology of area, we can estimate roughly how many layers are there, or the dominant layers. How many unconfined layers will be there? There's only one, right? Because the surface is on the top, and under the surface, at once when you come in, it is the unconfined aquifer. So most probably the unconfined aquifer is on the top, and even if you have an impervious layer on the top, there will be a very small unconfined aquifer or an unconfined unit. Okay, so only when this confining unit is coming out or jutting out, then you don't have a unconfined aquifer. So at least one you will have, and at the most one. So you cannot have more than one unconfined aquifer, because the confining unit would be there and then another unconfined cannot happen. Confined aquifer may be present or may not be present. So for example, if there's no confining units and the surface is directly connected to the bedrock, then it is all a unconfined aquifer. So you don't have a confined aquifer in this case. Moving on. As I said, the unconfined takes days. Please remember this, 2 years. The confined aquifer, first confined below the unconfined, can take years, a couple of decades to centuries, whereas the deeper most confined aquifer can take millennia. The other types of recharge that can happen is by induced recharge. Okay, so for example, you can induce recharge through the process of pumping. But first, let's look at pumping, because pumping is an action of discharge. So groundwater discharge is the process by which you take water from the groundwater pool. And when you take it, there is the water table lowering and formation of cone of depression or drawdown. So this imaginary line is brought down because you are pumping water. So all the water here in this area is pumped out as discharge. Still recharge can happen, but the discharge is pulling the water, and part of the discharge which you apply to the field can come back as recharge. So the recharge source need not only be the precipitation, it can be your groundwater also. You pump groundwater, you put it on the surface, part of it is taken by plants, part of it recharges. Okay, so whenever we say discharge, it is the act of pumping or losing water from the aquifer. There is a natural discharge process, which we saw in the earlier slide. The natural discharge is the groundwater entering into the streams. That is called natural discharge, whereas this is called the pumping groundwater through groundwater discharge. Some more groundwater discharge images to discuss the fact that you can actually pull water from different resources within the aquifer. So here we have only one aquifer. It is the unconfined aquifer because the confining unit is at the bottom, and there is no aquifer on the top with a confining unit. Just one aquifer, and there is no confining unit on the top, so it is unconfined. You have ready recharge happening, infiltration, water moving down, and there are some contamination also. For example, you have a polluted lake or a polluted stream or a natural pollutant by geogenic contamination. I'll come to these terms later. But then you can also have a stream on the other side with water. So now what happens is when you start pumping, you pull water laterally into the groundwater well. So this is your well, and you have removed the screen here, which means water is moving inside. So you should understand that it not only pulls your groundwater, but as and along the table is being reduced. So this is the water table, and as and along the groundwater table is being reduced, it starts to pull water which are equal at the water table height. For example, this water in the stream. It may not pull this water which is far away, but it can easily pull this water because it is nearby, and the water table would be conducive to bring that water. The cone of depression is started because of the discharge, because of the pumping velocity, and because of that, there is a lot of lateral water moving inside. Okay, so the water table is lowered, and along with the groundwater, you may also pull the contaminated water or water from a lake or something. So that is why if you have a pump right next to a sewage system, let's say a toilet outside, and you have a well, some of the pumping by the well can also pull water from your septic tanks if it is leaking. So be careful of where you put the water wells. Same way, you can pull water from streams. So instead of water coming from groundwater into streams as base flow, now you are pulling the water from the stream into the groundwater well and extracting it as discharge. So let's break it. From the stream into the groundwater is called recharge, but the stream water, if it passes through the recharge and comes out into the well, it is discharge. Influence recharge and discharge is another important factor that we should look at, because when we discuss recharge and discharge, it is not at a small scale, because we are inducing recharge and discharge, or we are pumping using a motor or a pump, electric or solar powered pump. When you do that, what happens is you are actually pulling at a much faster pace, and you turn the dynamics or the gradient of groundwater flow. So initially the water table would have been here somewhere, okay, a straight line if you don't have the wells. Now you have the wells and it's opened here in the aquifer and you're pumping. How many aquifers do we have? We have only one aquifer. It is an unconfined aquifer, okay? An aquitard is there at the confining unit at the bottom. So what are we going to do is we are going to see an influence recharge and influence discharge. Okay, and because you start pumping here, Okay, because you pump at a very high rate, what happens is water from here would move into this well, which is an observation well. There is no pumping. You can see here there is no pumping, and it will go into this pumping well. So suddenly this well will get more water because it is being pulled from another suction, and that creates an artificial recharge first in the observation well. So first your water table goes up because you are pulling down, and then slowly when this water table goes down, then also this will come down. Okay, so the rate of water coming into the observation well, so we're just monitoring here, we're not monitoring here, the rate of water level recharge is induced by somewhere else pumping. Okay, you're pumping somewhere else, so it is inducing and causing the water to come into the well. Secondly, when you pump too much, when you continue pumping, then what happens? All the water inside your observation well is also going to be pumped. So initially it was recharging, but when you continue pumping, then you are going to pump all the water out, and that will be influenced discharge. So initially there's this water, there's no pumping. There is no point of losing water in this well, in the observation well. But why is it losing water? It's because surrounding area is pulling water. So this is the fact that even though you don't pump your groundwater, you would see your groundwater fall. And then the farmer asks the question, why is my groundwater falling when I'm not pumping? So it could be two reasons. One, the base flow, which means the groundwater is normally flowing, and so it might flow and reduce. Okay. But most importantly, the second factor is someone around you is pumping at such a high pace that it is influencing your wells and pulling all the water down. Initially, you would have seen a high water level, a good recharge, and then suddenly you're saying, oh, I'm happy, my wells are recharging even though it's not rainfall happening. But then as soon as that happens, you have to be aware that somewhere your water level is coming up. So sooner or later, if the pumping doesn't stop, your water level will plummet. And that is what happens. So for example, if you have industry pump, for example, it could be an industry for making, using a lot of water for a product, and or it could be a mass farming, or a water distribution plant where it takes on water for distribution. What happens is it can suck all the water at a higher volume, and when it takes all the water from this aquifer, from this water table, it influences the region around it, and that influence depends on the pumping rate and also the cone of depression that it causes. The cone of depression is, so for example, you have a water table like this, and here's where your pump is. So when you start pumping, it will fall down like this, the water table. And when it falls down, you get an initial recharge and then a discharge. But more importantly, the influence of the cone of depression goes as far as the material allows it to go, the solid material. For example, if water is locked in the aquifer, there's no connection between the rocks, then whatever you pump, it won't affect the nearby well. But if it is like an alluvial aquifer where it is well connected across the system, across the aquifer, then what happens is you pull down and you influence the neighboring wells. So you have to be very careful, and that is why if you take the water level readings in a particular village where extensive farming is happening, you don't see that only the village water level coming down. You see the neighboring villages also suffering and the water level coming down. The same doesn't apply for recharge, because recharge is a very slow process. It's not like one village recharges, all the villages around it will recharge. No, because it is very slow. However, pumping is a very fast rate, and when you pump, you indirectly influence the neighboring wells and pull out the water. That is your influence, discharge, and recharge because of anthropogenic stresses or actions. Let's look at the natural causes. Naturally, the water table is at the water table of the stream. Okay, so the level of the stream, or we call the stream stage, is normally at the same level of the water table in a good aerated environment, or an environment where there's good rainfall, there's good recharge, and the water table is healthy. Okay, so what happens in this kind of thing is, your water table normally would supply water from the groundwater into the stream, and that is where you see when you go to a river or a stream network, you see that the stream is at the lower elevation, and the mountains and ridges are there and water flows. So the water would be contributing to the stream, and that is natural discharge, which means water comes from your groundwater into the stream, which is natural discharge. For the stream, it is a positive, so it is called a gaining stream. The stream gains water from the water table. All this appropriately work on the pressure difference. Okay, so the water table is at a higher level, and therefore it has a higher potential, and water flows from high potential to low potential, which is at a lower elevation. So water flows from high elevation to low elevation in a stream. The water table is losing, the groundwater is losing here, it gives water, the volume is losing, and so it is called a natural discharge. The aquifer is losing water, it is natural discharge. The stream is gaining water, so it is called a gaining stream. The reverse of that is in a desert situation, where a stream is at a higher level than the groundwater table, and it is not readily influencing the groundwater table. Maybe the layer, the sediments and the rocks under the stream are making like an impervious layer. Okay, so that is why readily you don't see the water coming down, but slowly there will be water trickling. Why? The same principle. The stream water is at a higher potential than the water table, so water will be leaking. In this venue, it is called natural recharge for the groundwater table, whereas the stream is actually losing water, so it is called a losing stream. So here we have seen both natural recharge and natural discharge, where natural recharge happens due to the difference in the potential of where the water level is, and also because of movement of water from rainfall into the ground through gravity. We also saw induced recharge and induced discharge, where you pump water out of a system, gives you discharge of water, and it is induced. And also by inducing your pumping and inducing your discharge, you can also recharge some locations, and that is called induced recharge. So with this, we've covered the basics of some groundwater parameters, which are very important to discuss now in detail, how you estimate groundwater flow, etc., etc. I will see you on the next class. Thank you.